You're standing on the floor right now. Feels solid, right? Like it's pushing up on you, opposing gravity, keeping you in place. That's what your intuition tells you. But this is where physics gets strange because it's wrong, stunningly wrong. The floor isn't holding you up, not in the way you think, at least. Let's unpack this, and you'll start to see reality differently. Remember Newton's third law? For every action, there is an equal and opposite reaction. You push down on a floor, it pushes back on you. Seems obvious. But what they don't tell you about Newton's law is that it emerges from something deeper, and that changes everything. To see what's really going on, we need to zoom in, past the molecules, past the atoms, all the way down to the subatomic scale, where quantum fields roam, because that's where the real action is. Not in Newton's tidy equations, but in a seething ocean of quantum fluctuations, it gets even more disturbing. According to quantum field theory, those particles that make up the floor aren't just sitting there. They're not static little balls holding each other up like a microscopic game of Jenga. No, they're excitations in quantum fields blinking in and out of existence, interacting in a dizzying dance. And those interactions between excitations in the electron field, the quark fields, the photon field, that's what's really pushing up on you, not the floor itself, but the quantum fields that compose it, fields that permeate all of space, filled with quantum uncertainty and bustling activity. But it gets stranger still. Quantum field theory also tells us that empty space itself, the vacuum, is far from empty. It's alive with quantum fluctuations, particles and antiparticles popping into existence and annihilating each other in a never-ending frenzy. And here's the kicker. Some of those vacuum fluctuations are interacting with the quantum fields that make up the floor and your feet. In a sense, empty space itself is pushing up on you too, ever so slightly. Chew on that for a minute. So the solidity you feel, the firmness beneath your feet, emerges from a microscopic maelstrom of quantum activity. The floor's apparent stability is an illusion, a helpful fiction obscuring the true nature of the subatomic world. The real problem isn't that Newton was wrong. His laws work spectacularly well at everyday scales. The problem is that they're incomplete, an approximation of a deeper quantum reality. A reality where objects are not static and space is not empty. And this points to a profound truth. Beneath the veneer of our classical intuition lies a universe that's utterly alien to our evolved conceptions. A universe governed by the strange rules of quantum mechanics, where fields and fluctuations reign supreme. So the next time you take a step, remember, the floor isn't pushing back on you. Quantum fields are. And they're doing it in a way that would shock Newton to his core. But this is just the beginning. Before we go any deeper, I need to ask you something. If you're here for comfort, this isn't the channel for you. But if you're here for truth, even when it's unsettling, take a second to support this mission. Hit like, subscribe, and leave a comment telling me what part of reality shocked you most. Every interaction tells the algorithm that depth matters more than distraction, and that thinking clearly still has value. If you want to keep tearing apart reality with me episode after episode, make sure you're following. We're just getting started. When you stand on a floor, you might think it's the firmness of the material that's holding you up, resisting the pull of gravity. But the real story is far more profound and bizarre. To understand why, we need to confront the true nature of force itself. Since Newton, we've imagined forces as tangible things, invisible tethers that push and pull on objects. But the quantum world tells a different story. In the subatomic realm, forces are not instantaneous and direct. They're mediated by particles. Well, take the electromagnetic force, the one that keeps electrons orbiting atomic nuclei and binds molecules together. In quantum field theory, this force is carried by photons, the fundamental particles of the light. But how can a particle, something localized and small, give rise to a force that seems so pervasive and constant? The answer lies in the mind-bending concept of virtual particles. These are not particles in the usual sense. They're more like quantum ghosts, flickering in and out of existence, borrowing energy from the vacuum itself to briefly manifest and interact with real particles. It's these virtual photons constantly shuttling back and forth between charged particles that create the illusion of a continuous electromagnetic force. Each individual exchange is fleeting and insubstantial, but the cumulative effect is the familiar force that holds the atoms of your feet and the floor together. But it gets stranger. In quantum field theory, particles are not the fundamental entities. They're excitations of underlying fields that permeate all of space and time. Electrons are ripples in the electron field, photons in the photon field, and so on. These fields are the true bedrock of reality. So when the floor pushes up on you, it's really the quantum fields that compose the floor interacting with the quantum fields that compose you. And they interact through a ceaseless dance of virtual particles, popping into existence, mediating the force, and then vanishing back into the quantum foam. This interaction is happening everywhere, all the time, between the countless particles that make up your body and the floor, and between the particles in the floor and the Earth's center, between electrons in distant stars and protons at the edge of the observable universe. The cosmos is a vast interconnected web of quantum fields communicating through the language of virtual particles. This picture completely upends our classical notion of empty space. In Newton's universe, space was a featureless stage where objects interacted across a void. In Einstein's universe, space became a malleable fabric, warped by mass and energy. But in the quantum universe, space is not empty at all. It's alive with quantum fields and virtual particles, a seething ocean of possibility and flux. And this realization raises profound questions. If empty space is not truly empty, but rather suffused with an ever-present quantum medium, could we harness that medium? Or could we use it to transmit information, to compute, or even, as some speculative theories suggest, to give rise to consciousness itself? These are not idle fantasies, but active areas of research at the frontiers of theoretical physics. Some scientists posit that information is the fundamental currency of the universe, and that the quantum fields that fill empty space are the ultimate hard drive. Others suggest that the interplay of virtual particles in the vacuum could give rise to exotic new states of matter, or even to entirely new universes. But to fully explore these mind-bending possibilities, we need to confront perhaps the deepest implication of quantum field theory. The idea that space and time themselves may not be fundamental, but rather emergent properties of something even more profound. If you're feeling disoriented, unmoored from your classical intuitions, embrace that feeling. Because in the quantum realm, the rules we take for granted break down, and reality becomes a hall of mirrors, each one reflecting a deeper, stranger truth. Keep following the path. The rabbit hole goes deeper than you can possibly imagine. In the quantum realm, our intuitions about space and time break down. To the smooth, continuous fabric of space-time that Einstein envisioned becomes a seething foam of quantum fluctuations at the smallest scales. And this hints at an even deeper truth. Space and time may not be fundamental at all, but rather emergent properties of something more profound. To understand this, we need to dive into one of the most mysterious and bizarre objects in the universe: black holes. These cosmic behemoths are usually thought of as destructive monsters, ripping apart anything that falls into their clutches. But in the 1970s, Stephen Hawking dropped a theoretical bombshell that changed everything. Hawking showed that black holes are not entirely black. They actually emit radiation, slowly evaporating over unimaginably vast timescales. This Hawking radiation arises because of the strange effects of quantum fields and extreme gravity. At the event horizon, the point of no return around a black hole, the intense gravitational field distorts the quantum vacuum, causing virtual particle pairs to separate. One particle falls into the black hole while the other escapes as real radiation. Over time, this trickle of escaping particles causes the black hole to evaporate. But here's the kicker. As the black hole evaporates, it appears to take information with it. All the details about what fell into the black hole seem to be lost forever, swallowed up by the singularity at the center. And this poses a huge problem for quantum mechanics. One of the bedrock principles of quantum theory is that information cannot be lost. It can be scrambled, entangled, and transformed, but never destroyed. So how can a black hole simply erase information? This is the famous black hole information paradox, and it's been keeping physicists up at night for decades. But in recent years, a new perspective has emerged that could resolve the paradox and revolutionize our understanding of space and time. It's called the holographic principle, and it's as mind-bending as it sounds. The basic idea is that all the information contained in a volume of space can be described by a theory that lives on the boundary of that space. Just as a hologram encodes a three-dimensional image on a two-dimensional surface, the universe could be a holographic projection of quantum information encoded on its horizon. In this view, space itself is not fundamental, but rather emerges from the entanglement of quantum bits, qubits, on the boundary. The smooth three-dimensional space we experience is a kind of illusion, a projection or reconstruction from the two-dimensional hologram at the edge. And black holes are the ultimate test of this radical idea. According to the holographic principle, a black hole's information is not lost, but rather encoded on its event horizon. As the black hole evaporates, that information is gradually released in the Hawking radiation, preserving the quantum mechanical rule that information must be conserved. This is a staggering thought. It suggests that reality as we know it, the three-dimensional space we move through, the linear time we experience, is not the whole story. It's a higher dimensional projection, an emergent property of a deeper quantum code. But it gets even stranger. If space is emergent, what about time? Could the arrow of time, the inexorable flow from past to future, also arise from the entanglement of quantum states? Some cutting-edge theories suggest that time itself may be a holographic projection, a kind of cosmic movie that we're all embedded in. In this view, the universe is like a vast quantum computer, processing information on its boundary and generating the flow of time as a computational output. The past, present, and future are not absolute, but relative to the entanglements between quantum subsystems. And this could shed new light on one of the deepest mysteries in physics, the origin of the universe itself. If space and time are emergent, then the Big Bang may not be a true beginning, but rather a transition, a moment when the quantum code of the universe began to be processed, unfolding the cosmos we see today. These ideas are still highly speculative at the forefront of theoretical physics, but they hint at a profound shift in our understanding of reality. The universe may not be a stage where events play out, but rather a vast cosmic hologram where space, time, and matter are projections of a deeper quantum reality. And if this is true, it raises questions that strain the limits of human imagination. Could we hack the cosmic code, altering the hologram of reality? Is our universe one of countless projections, each with its own laws and constants? And might we ourselves be holographic projections, our consciousness emerging from the entanglement of quantum bits at the edge of reality? These are the kind of questions that keep physicists awake at night, staring into the void and wondering if it stares back. Because in a holographic universe, the void is not empty. It's the source code of reality itself, the ultimate answer to the question of why there is something rather than nothing. But to even begin to approach these questions, we need a theory that can unify quantum mechanics and gravity, that can describe the quantum code of the cosmos. And that's where the cutting edge of physics is right now, the search for a theory of quantum gravity, a theory of everything that could finally reveal the true nature of reality. In the next and final part, we'll venture to the far reaches of theoretical physics, to the strange realms of string theory, loop quantum gravity, and beyond. We'll confront the ultimate question: what is the fundamental code of the universe, and what does it reveal about the nature of existence itself? Buckle up and hold tight to your sense of reality, because where we're going, there are no maps, no signposts, only the shimmering haze of the quantum unknown. But if we're brave enough to follow the equations, to let go of our classical intuitions, we just might catch a glimpse of the ultimate truth, the cosmic code that underpins the fabric of the universe. So ask yourself, are you ready to take the red pill, to wake up from the illusion of classical reality and dive into the rabbit hole of the quantum cosmos? If so, follow the path. The journey is just beginning. In the quest to understand the fundamental nature of reality, there's a threshold where physics ventures into the realm of metaphysics, where equations brush up against the eternal questions of existence. And at the forefront of this quest is the search for a theory of quantum gravity, a theory of everything that could unify the laws of the large and the small and reveal the quantum code of the cosmos. The two pillars of modern physics, quantum mechanics, and general relativity describe the universe with unprecedented precision, but in fundamentally different ways. Quantum mechanics paints a picture of reality that is probabilistic, where particles can be in multiple states at once, and entanglement weaves the fabric of the subatomic world. General relativity, on the other hand, describes gravity as the curvature of spacetime, a smooth, continuous geometry that determines the motion of planets and the fate of stars. But these two pillars are not compatible. In the extreme environments of black holes and the early universe, where quantum effects and gravity both come into play, they break down, leading to nonsensical infinities and paradoxes. To truly understand the nature of reality, we need a theory that can reconcile these two descriptions, that can paint a picture of space-time that is fundamentally quantum. This is the realm of quantum gravity. And there are several contenders for this ultimate theory. One of the most promising is string theory, which posits that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings of energy. Just as the vibrations of a violin string create different notes, the vibrations of these fundamental strings create the different particles and forces we observe. But for string theory to be consistent, the universe must have more than the three spatial dimensions we're familiar with. In fact, it requires 10 or 11 dimensions, with the extra dimensions curled up into tiny, complex shapes called Calabi-Yau manifolds. In this view, what we experience as particles are actually vibrations in higher dimensional space, like the notes of a cosmic symphony playing out in dimensions we cannot see. Another approach is loop quantum gravity, which starts with the principles of general relativity and quantizes space-time itself. In this theory, space is not a smooth continuum, but a network of discrete loops, a kind of quantum mesh, where area and volume come in tiny, indivisible units. In the same way that a digital image emerges from discrete pixels, the smooth spacetime we experience emerges from this quantum geometry at larger scales. Both of these theories, and others like causal set theory and non-commutative geometry, paint a picture of reality that is deeply alien to our everyday intuitions. They suggest that at the most fundamental level, reality is not a stage where events play out, but a vast cosmic computation processing quantum information in higher dimensions or discrete loops of space-time. But perhaps the most profound implication of quantum gravity is what it suggests about the nature of time. In Einstein's relativity, time is relative, warped by motion and gravity, but it still flows inexorably from past to future, carving the universe into moments. In quantum gravity, however, time may not be a fundamental property of the universe at all. In theories like the Wheeler-DeWitt equation and the no-boundary proposal of Hawking and Hartley, the universe is described by a quantum wave function that exists in a timeless, abstract space. Time as we know it emerges only as an approximate property at larger scales, a kind of illusion born from the entanglement of quantum subsystems. The flow of time, the very notion of past and future, could be a secondary phenomenon, a side effect of the way quantum information is processed in the cosmos. This is a staggering thought. It suggests that at the most fundamental level, reality is atemporal, that the universe exists in a kind of eternal now, a timeless state of quantum possibility. The flow of time, the narrative of cosmic history, is something that emerges from this timeless substrate, like the flow of a river emerging from the quantum foam of spacetime. And this raises profound questions about the nature of causality, free will, and the very notion of a beginning or end to the universe. In a timeless cosmos, the Big Bang may not be a singular event, but one of countless quantum fluctuations, a local eruption in the eternal quantum froth. And the ultimate fate of the universe, the end of time itself, may be a meaningless concept, a category error in a reality where time is not fundamental. These are the kind of ideas that stretch our minds to the breaking point, that push us to the very limits of intellectual and imaginative possibility. They suggest that reality at its deepest level may be so alien to our evolved conceptions, so far beyond our intuitive grasp, that we may need entirely new modes of thought, new languages, new forms of mathematics to even begin to comprehend it. And yet, this is the great adventure of science, the noble quest to understand the nature of existence itself, to stare into the cosmic void and to ask what is real, what is the fundamental code of the universe, and what does it mean for us, for our place in the grand scheme of things, for the meaning and purpose of our fleeting existence in this vast, strange cosmos. These are questions that may never have final answers, that may forever recede into the misty horizons of knowledge. But the quest itself, the courage to ask, to probe, to imagine, is what defines us as conscious beings, as creatures of curiosity and wonder. So as we stand on the brink of a new physics, a new understanding of reality, let us embrace the vertigo of the unknown, the dizzy exhilaration of venturing into uncharted realms of thought. Let us be bold in our questioning, relentless in our pursuit of truth, and humble in the face of the cosmic mystery. And above all, let us never lose sight of the sheer, staggering beauty of this grand cosmic dance, this play of quantum shadows on the screen of space-time. For in the end, that may be the deepest truth of all, that we are part of something vast and ancient and utterly beautiful. A universe that is not just stranger than we imagine, but stranger than we can imagine. If this journey into the quantum unknown has left you with more questions than answers, more wonder than certainty, then welcome to the cutting edge of human knowledge. This is where the map ends and the territory begins. This is where we venture into the wild, uncharted lands of the mind, armed only with our courage, our curiosity, and the steadfast belief that truth, no matter how strange or counterintuitive, is always worth pursuing. If you've made it this far, congratulations. You've taken the red pill. You've looked behind the curtain of reality. There's no going back now, but there's going forward into the strange, beautiful, endlessly fascinating labyrinth of nature, into the quantum realm where nothing is what it seems and everything is possible. So keep asking the big questions. Keep probing the foundations of reality. And above all, keep marveling at the sheer, staggering improbability of it all. The fact that in a universe so vast and old and strange, creatures like us can emerge from the quantum foam, can look up at the stars and wonder, can trace the cosmic code all the way down to the bedrock of being. This is the great adventure of science, the great story of human curiosity. It's a story that has no end, only new beginnings, new mysteries to unravel, new wonders to behold. And in the telling of this story, in the pursuit of these cosmic questions, we become part of something grander than ourselves, a legacy of inquiry and imagination that stretches back to the dawn of human consciousness and forward to the horizons of the unknown. So stay curious, my fellow travelers in spacetime. Keep chasing the light of truth into the quantum shadows, and never, ever stop wondering at the sheer dizzying beauty and mystery of this strange cosmic dance we find ourselves in. The floor may not be holding us up, but something much grander, much deeper is, and it's inviting us with every quantum flutter and every cosmic swell to join in the great adventure of understanding, to trace the quantum threads that weave the fabric of reality, and to marvel at the cosmic tapestry they reveal. The journey continues, the story goes on, and we, the improbable products of quantum chance and cosmic necessity, have the unimaginable privilege of being part of it. So let's make it a story worth telling, a journey worth taking, a universe worth marveling at. And let's never, ever stop asking, what's really holding us up? What's at the bottom of it all? Because in the end, that may be the deepest question of all, and the one most worth pursuing, down all the quantum rabbit holes and across all the cosmic vistas of this strange, beautiful, endlessly surprising universe we call home.